Witness, Engineer Sotomayor Oscar, and classmate. Today our group will present the analytical solution of the one-dimensional heat equation using the method of separation of variables. The heat equation is a partial differential equation that describes how temperature changes over time inside a solid object. In our project, we consider a rod of length L with homogeneous Newman boundary conditions. These boundary conditions mean that no heat enters or leaves the ends of the rod. Therefore, the rod is perfectly insulated. The initial temperature distribution is represented by the function fx, and our objective was to find the temperature at any position and any time. There is a physical description. We analyze the thermal profile in a homogeneous one-dimension medium of linear and L subject to thermal insulation and it ends. The assumption of adiabatic ends translates mathematically into homogeneous Newman-type boundary conditions, indicating zero heat flux to the exterior environment. Here is a mathematical formulation and the subject to the following constraints: the adiabatic boundaries and the initial profile. Next, my partner Edison Ibañez.
Separation of variables and variables problem. The first step was applying the method of separation of variables. We assumed that the solution could be written as the product of two functions, u x t equal x times t. This assumption transforms the partial differential equation into two ordinal differential equations. Next, we solve the special equation, which becomes an eigenvalues problem. Next slide, please. We analyzed three possible cases: negative eigenvalues, zero eigenvalue, and positive eigenvalue. Only the zero and positive eigenvalue produce non-trivial solution. Next slide, please. Finally, we obtain the eigenvalues lambda n equal np about L squared, and the corresponding eigenfunction xn equal cos npx about L. Next, my partner Albeiro.
Well, in temporal equation and thermal damping. In this section, we have 3 points. First, temporal, one solution, Tn on function of t equal am for exponentially elevate minus alpha cuadrado for mp about L all cuadrado for t show exponential decay over time governed by thermal diffusion of alpha cuadrado. Second, constant mode for n equals 0, t of 0 in function of t equal a0 remains constant over time, representing the final state equilibrium. Conserved thermal mass. And third, high frequency mass for n more equal 1, decays rapidly due to the m quadrado, depending quickly, smoking out spatial temperature irregularities. Next slide, please. Okay, Fourier analysis and coefficients. In this section, we have 3 points. Initial condition, t equals 0 expands the initial profile into a Fourier cosine of zeros in function f of x equal a0 about 2 at summatory of n equal 1 and infinite of am coseno to mpx about L. Second, average term of A0 equal to about L of integral to 0 to the L. Fx dx gives the average initial temperature. And third, harmonic coefficients An insulate via orthogonality of An equal to about L of integral to 0 of the L to the function f of x coseno mpx about L. The x determines the amplitude of each spatial mode. In conclusion, we analyze a thermal rod with insulated ends. The Sturm Liouville spatial problem yields a discrete spectrum of cosine eigenfunctions that satisfy the zero-flux boundary condition. Temporally, these modes decay exponentially with higher spatial frequencies, smoking out, out almost instantly. Through Fourier's analysis and orthogonality, the constant term of A0 about 2 give us the final state equilibrium temperature, while coefficients Am represent the initial spatial fluctuations. Next up, my partner Michael Lalvay.
To verify our solution, we check our important conditions. First, we substituted the solution in the Git equation. The left-hand side and the right-hand side were equal, so the differential equation was satisfied. Next slide, please. Second, we verify the boundary conditions since the derivative of the cosine function is the sine function and sine 0 equals 0 and sine pi equals 0. Both Neumann boundary conditions every satisfied. Finally, we evaluated the solution obtained t equals 0 and recovered the ordinal function. This confirms that the initial condition is also satisfied. Next up, Adrian.
Okay, we will see the physical meaning of this equation. So, as my friends said, imagine a metal rod that is perfectly insulated. Initially, one part of the rod is hotter than the rest. As time passes, heat spreads from the hotter region to the colder regions. The higher Fourier modes disappear quickly, while the lower modes remain for a longer time. Eventually, the entire rod reaches a uniform temperature. Because the rod is isolated, no thermal energy leaves the system. Next slide, please. Finally, we conclude that the method of separation of variables is an effective analytical technique for solving the one-dimensional heat equation. The eigenvalues, eigenfunctions, and Fourier coefficients are essential for constructing the solution. Moreover, the analytical solution accurately describes the physical process of heat diffusion until thermal equilibrium is reached. That's all for today. Thank you very much for your attention, and we will be very happy to answer your questions.